a closed form for the question that says UN plus 2 minus 6UN plus 1 plus 9 UN is equal to 7 to the power of 3n, like this. So as you can see, we said this is a non-homogeneous second order recurrence. So in order to solve this, we need to split it into two things. First of all, we need to find the solution of the what? Of the homogeneous part. So the homogeneous part is this one. So we actually need to find the solution of the homogeneous part, okay? Which is the corresponding homogeneous part is UN plus 2, 6UN plus 1, plus 9UN is equal to 0. So the characteristic function of this homogeneous part is what? Is R squared, right? Minus 6R plus 9 is equal to 0. Solving this gives us what? Looks like it's a perfect square. R minus 3 squared is equal to 0. So R is 3. So it is a repeated root, isn't it? Twice. So if it is repeated, we already discussed why we follow that order. We are going to follow which order? UN is equal to A, correct? Plus what? Bn in brackets, then what? Then alpha to the power of n. So in this case, what do we have? We're going to have UN is equal to A plus Bn, then 3 to the power of n. Are we together? Then we will look at the what? What do we call this? This is the complementary function, isn't it? Okay, we are going to look at what now? The particular solution. So the particular solution, because it is guarded by this form. And not only this form, it is also guarded by the roots here. So we can actually see that the particular solution has something else here. 3 is the same as that. So what are we going to do? Lambda n squared 3 to the power of n. Why did you put n squared?
Because it's a repeated root.
Mm-hmm. So alpha is equal to beta is equal to alpha. Yeah. So alpha is equal to beta is equal to this value here, p. That's the form. Because we said if we've got a form, here is the table, and I said you can actually have a situation whereby you can try it to use, remember, this is an exponent. So you can actually start by trying to use UN is equal to what? Lambda 3 to the power of n. You see that? When you try to use this into this solution, it's going to fail. That's your cue that tells you that something needs to be done. Let's say you've forgotten all these steps of this is equal to that. You see these two are equal. So you can actually substitute the form of the particular solution here in here. And then when you try to solve it, let's just try to do it for the fun of it. We see that what's going to happen here? We're going to have lambda. Okay, we're going to have lambda n plus 2. So it's going to be lambda 3n plus 2 minus 6 lambda 3n plus 1 plus 9 lambda 3n, isn't it? Is equal to what? 7 3n. So we can cancel out the 3n. All right. So this is 3 squared, that's 9. So 9 lambda here. This is 3 times 3, that's minus 18 lambda here. This is plus 9 lambda here is equal to 7. But you see what's happening? we are going to have 0 is equal to 7. That's not workable. So that's why this form is not going to work, because of the repetition. That is, we have got alpha is equal to beta, which is also equal to p. Do you see that? So we have to, if you put another n, it's still going to fail. So you can say, because this has failed, I mean, you can try and error if you've forgotten this, because these are the type of questions that are actually preferred in the exam. So you can say, okay, let me add another n here, because this one is failed. So I'm going to add another n, have this, and see if we can win it, isn't it? You will see again, you're going to have lambda n plus 2, 3n plus 2, minus 6, lambda n plus 1, 3n plus 1, plus 9 lambda n 3n is equal to 7 3n. You can expand if you want, or you can start by removing the 3n. If you remove the 3n here, you're left with 9 lambda n plus 2. Do you see that? If you remove the 3n, the 3 here, you're going to be left with 3 times 3. That's minus 18 lambda n plus 1. Then you're just going to be left with plus 9 lambda n is equal to 7. Expanding again gives you 9 lambda n plus 18 lambda minus 18 lambda n minus 18 lambda. Is that so? And what about that? That's plus 9 lambda n is equal to 7. So what do we have? 9 lambda and 9 lambda here. That's 18 lambda n, isn't it? 18 lambda n, then these two cancel. Okay, everything else cancels again. You get 0 is equal to 7. So you can see it doesn't work. Do you see that? I just want you to be fully convinced why we are using n squared here. So you can see it doesn't work eventually. So this is the form that we're going to use, right? So we're going to have now lambda n plus 2 squared. Then what? 3n plus 2. Placing this here, you just put n plus 2 where there's n plus 2, isn't it? N minus 6 lambda, okay? Then n plus 1, then 3n plus 1, plus 9. Did I do something? Yes, that's a squared here, right? Yeah. Squared here. Plus 9 lambda n squared, 3n is equal to 7 3n. Okay, yes, we have the choice to remove the, to cancel out the 3 to the power of n here. So when we cancel out the 3 to the power of n, we're actually going to have, I'm sure you can see where I'm getting the 3 to the power of n by just separating exponential laws. So that's going to be 9 lambda here, then n plus 2 squared minus 18 lambda, then n plus 1 squared plus 9 lambda n squared is equal to 7. This one now is going to work perfectly fine. Okay, it just appears to be long, but it's going to work perfectly fine, because we are going to have n squared plus 4n here plus 4 minus 18 lambda here, n squared plus 2n plus 1 plus 9 lambda n squared is equal to 7. So we're going to have 9 lambda n squared plus 36 lambda n plus 36 lambda minus 18 lambda n squared minus 36 lambda n minus 18 lambda plus 9 lambda n squared is equal to 7. Let's check what is cancelling and what's not cancelling. So there's 9 lambda n squared, there's another 9 lambda n squared here. When I combine them, okay, let me just write it down. 12. So we're going to have 18 lambda n squared minus 18 lambda n squared, isn't it? Then we've got 36 lambda here. This one will cancel this one, correct? And this one is going to be with this one. So that's going to be 36 minus 18, which is just 18 lambda is equal to 7, right? So eventually we are going to get lambda is equal to 7 over 18. Okay. What does that mean now? That means un is equal to a plus bn 3 to the power of n plus the particular solution, which is 7 over 18 n squared 3 to the power of n, like this. That's your final answer. All right? Make sense? Now I'm not doing the part of finding a and b because that is straight away, because you're going to use the initial conditions that are on the board there. U naught is equal to 1 and u1 is equal to 4. That's all to find a and b. But what is very important is understanding how do you go about finding this. All right? Now, like we said, we have done that part where we're verifying these solutions. So we can actually verify that a closed form is a solution of a recurrence, isn't it? By what? By substituting the closed form into the recurrence relation. And if it gives you the same form, then it is a relationship. It is a solution, isn't it? Another way to see that, you can prove that a closed form satisfies a given relation using what? Your favorite method, which is what? Mathematical induction. You can actually do induction to prove that this is a solution as well. So how do you do that? That's what is very important. How do you do that? Let us look at this question. I'm sure you can write it down. We is told that 2 minimum number of moves dn needed to transfer n disk from one peg to another in the tower of Hanoi problem is given by this. So no need to understand the problem itself, because already everything is given. We just want to solve the problem. Okay, so this is the recurrence relationship, and this is the initial condition. We need to prove that this closed form, this is our closed form, is a solution. So technically we need to be what? Substituting to see that it is a solution, isn't it? Like well, by substitution, I mean you could just say dn is equal to 2, then you put 2n minus 1, is that okay? Plus 1, like this. Do you see that? Then you get what here? What are you going to get? You're going to get 2n minus 2 plus 1, then you get 2n minus 1. Proved. It is a solution. Correct? But that's not the method we're using right now. This is the method we did previously. Okay? We are going to use induction. So when we're using induction, what do we do? So you, first of all, you're given what? You're given what? You're given initial condition. Or maybe I should say use. Maybe I should say use given initial condition. So you're going to use the given initial condition first. What is the given initial condition? D1 is equal to 1. So this forms our basis. So our basis, we are going to say n is equal to 1. D1 is equal to what? 2 to the power of 1. We get that? Substitute that into the closed form. Minus 1, which is just 1. Are we together? So, and D1 is what? 1 here. So if we put n is equal to 1 here, we still also get 1. What can we say about that? So we can say the closed form is true. The closed form is true for n is equal to 1. Are we together? So that's my basis. Next point is to go to the assumption step. Okay. What are we doing for the assumption step? We are assuming, so we assume the closed form is what? Closed form is true. For what? For n is equal to k. Is that so? In other words, we are saying d to the power of k is equal to 2 to the power of k minus 1. So our assumption is always easy to make, isn't it? Then the next step is to go to the inductive step, or the induction stage. What do we want to prove? We want to see if it is true, right? We want to prove if it's true for what? For n is equal to k plus 1. But obviously, like I always say, you already know in somehow when you're doing induction, I prefer this. What is it that you're required to prove? It's 2k plus 1 minus 1. That's what we are required to prove. So we are working with the answer already. So we are required to prove that 2k plus 1 minus 1. So what do we do now? So we take n is k plus 1. We place it in here, isn't it? In this recurrence relation, and see if it reduces to this point. So we're going to have d, where there is n here, I'm placing k plus 1. Then 2, where there is n here, I'm placing k plus 1. So if there is n minus 1 here, if you put k plus 1, what does it become? I'm saying here, look here, it's d, isn't it? So where there's n, I'm putting what? K plus 1, then minus 1 plus 1. Is that so? Does that make sense? Does that make sense? You're just substituting where there's n, you put k plus 1. So in fact, this reduces to 2dk plus 1. Do you get that? But now, we know what is dk from our assumption. What is dk? 2 to the power of k minus 1. So we substitute that dk. Now we're going to get 2k plus 1 minus 2 plus 1, which is equal to 2k plus 1 minus 1. Is it what we were expecting? The answer is yes. Isn't it? Now, let me just write it here because I don't have space anymore. You do your conclusion. So what can we say? So is so true for what? For n is equal to k, isn't it? It's true for n is equal to k, and it is implies that it's also true for what? For n is equal to k plus 1, and true for n is equal to 1, and true for n is equal to 1. Then you make that conclusion. Therefore, by induction, the closed form, this is how you write it. I have to write it all. The closed form dn 2 to the power of n minus 1 is true for all n element. N now is not an integer in this case because n is referring to position. So n is always an element of the natural numbers. You see now? So you can prove that is true by induction as well. Okay? Are you done? Next question. Okay, write it down, then we go through it together again. Write it down quickly. Write it down, then we go through this together as well. All right, so basis step. Our basis step is starting from where? It's always being guided by this condition. So our basis step is starting from when n is equal to, in this case, n is equal to 0. So when n is equal to 0, what do we have? U0, we substitute here, is going to give us 0, 0 plus 1 over 2, which is 0. So it's true, isn't it? Okay? You can make a comment. The closed form is true for n is equal to 0. You make an assumption. Before you do induction, you need to have an assumption. You make an assumption. Assume the closed form is what? Is true for n is equal to k. So if we assume that is true for n is equal to k, it means we are going to have uk is equal to k plus 1 over 2, and the condition is still the same. K must be greater than or equal to 0 there. Okay? I'm sure by now you can see, you know what you need to prove. So even if you can write it here, your RTP, you need to prove that k plus 1. Then if I put k plus 1 here, I'm going to get k plus 2 inside the bracket. So this is what I am aiming to achieve. This is what I'm aiming to achieve. Okay? So I can't go wrong if I know already what I'm working with. I can't go wrong, all right? So let us see if we can do that. Induction stage. Induction stage. Your induction, okay? So what are we going to do with the induction stage? Just like we've done here, to prove that if it's true for n is equal to what? To prove if the closed form is true for n is equal to what? K plus 1. Now, is it true for n is equal to k plus 1? Yes, we substitute k plus 1 here. We get u, correct? We get u, because it's u, k plus 1. If you put k plus 1 here, you get uk, isn't it? Is that okay? Then if you substitute k plus 1 here, you're just left with k plus 1. But we already know what is uk from our assumption. That's k plus 1 over 2 plus k plus 1, like this. So we need to see if we can manipulate this expression to give us this one in green here. So it's going to be k plus 1 over 2, everything to one denominator, isn't it? Plus what? 2k plus 2, like this. So what are we going to have here? K squared plus k plus 2k plus 2 all over 2, which is k squared plus 3k plus 2 over 2. That's another way. You can just factorize this is k plus 1, k plus 2 over 2. Then the conclusion, as I've always said, is important in induction. It's not just the working. So if this is like 5 marks, you get a mark here, you get a mark here, you probably get 2 marks here, then that's it. If you don't conclude, that's it. So the conclusion is very important because it's not true if you don't conclude. You've got to make a conclusion at the end. So you're going to write your conclusion. And it's repetition. You find ways to frame it the way you want. It is true. So if it's true for n is equal, if it's true, I'm changing my wording now. If it's true for n is equal to k, it implies that it is also true. Also true for n is equal to k plus 1 and n is equal to 1. Therefore, by induction, the closed form in this case is our un here. n plus 1 over 2 is true for all n element of the natural numbers. Happy? So that's basically the induction part. You can prove by substitution, but if the question is clearly stated that use induction, so even if you substitute this in here, you don't get marks because you didn't use the correct method. All right? So that's how you do induction. Now let us check what's important when you're doing induction for what? For second order, because this is all induction first orders. You can see that. So how do you do induction for second order? It's the same steps. The only difference is you realizing that when we are doing second order, we have been provided with what? With two initial conditions, because your recurrence, your recurrence relation here is now in two steps, isn't it? So it's a second order, so you must have two initial conditions. So that is very important. So you've got two initial conditions in your assumption step, okay, before you do your inductive step. Okay, that's what you need to do. So can you quickly copy example number 23 before I give you the opportunity to do example number 24? So your basis, you start with n is 0 because we've got 0 here, right? Then it's not a here, it's not u here, it's a. You go to u, a0 is going to be 3, 4 to the power of 0 minus 2 to the power of 0, which is going to be 3 plus 1, which is 4. That's true. Okay? You go to n is 1, you're going to have a1, which is 3, 4 to the power of 1, minus 2 to the power of 1, which is going to be 12 minus 2, yes, which is 10. You see that? So these two statements tells us that the closed form is true. Is true for what? For n is equal to 0 and n is equal to 1. All right? For n is equal to 0 and n is equal to 1. So we go to our assumption step now. We make an assumption. What is the assumption going to look like? We've got two conditions, isn't it? So we assume for what? Assume it's true. Assume it's true for which is true for n is equal to what? K is the last term, right? And what else? N is equal to k minus 1. That's very important because it's from 0, first term, initial conditions 0 and 1. So we go there from k, we go move backwards. K minus 1 is after k, isn't it? Before k, rather, sorry. Okay, so that's our assumption. Is true for that. Okay. In other words, we are saying AK. If AK, what is it going to look like? AK is going to look like 3 to the power of 4k, and then what else? Minus 2 to the power of k, and we're going to have ak minus 1. So if I put that in there, it's going to be 3, 4k minus 1 plus minus 2k minus 1. These are the two steps we have in our assumption. So we are going to use that in making our inductive step in induction, in our induction now. So we go to induction. Automatically, you actually know what you are required to prove here. If you are to write it aside, we are required to prove what here? It's going to be equal to what? AK plus 1. Yeah. 3, 4k plus 1. Yes. So you're working with this. You can temporarily just box it in here, so that whatever you're doing, this is already guiding all your steps. So we're working with this. Now let's go to our inductive step. So we're going to have AK plus 1 on that function, AK plus 1. If I place k plus 1, there is going to be 2 AK plus 8 AK minus 1, like this. I'm using the original recurrence now, the recurrence relation. This is coming from AK. It's coming from AK. It's coming from AN is equal to 2AN minus 1 plus 8AN minus 2, like this. All right. So then from here now, we are going to have 2, but we do have AK. What is AK? It is 3, 4 to the power of k plus minus 2k, okay? Plus 8 AK minus 1, which is this one, 3, 4k minus 1 plus minus 2k minus 1. That's what you have here. So you are basically going to do whatever you do, your steps into trying to get what is here in black color. So if I to expand this, that's the first thing to do, is to get 6, 4k plus 2 minus 2k plus 24. 8 times 3 is 24. 4k minus 1 plus 8 minus 2k minus 1. All right. So that looks like we've got something else. What do we have now? What are we going to do with the next thing? You're going to separate 4k minus 1. So we're going to get 4 to the power of k here, 6, 4 to the power of k. Then what else do we have? Are we going to take this one? No. Mm-hmm.
Divide the 24 by 4. Yeah. That's plus 6.
So you want to divide the 24 by 4. It's going to give you 6 and 4. 6 here. So this is going to be what? 6, 4 to the power of k. And what about this one? This one becomes minus 4.
Yeah, because minus 1 and 2 isn't.
Where are you getting that?
Minus 2 pound minus 1 is minus half.
You're saying minus 2 to the power of minus 1.
Is minus half.
Yeah, it's minus half, yeah?
Yeah, so times by 8 is negative 4.
So it's going to be minus 4 minus 2 to the power of what? K. So we have eliminated the K, the minus 1's here. So what is the next step now? If we combine, does it give us what we want? 12, 4K. That's fine. Then this was going to give us minus 2 to the power of K. Then we have to do something here because we want plus 1. So we have to take out the 4 in the 12. That's going to be 3, 4K plus 1. Then obviously here we are fine, isn't it? Because that's a plus here. We take it. Then there's going to be minus 2K plus 1. Then you go to the last part, which is the conclusion. Good. All right? Did I hear the easy part?
Deductions there.
I like that part, to hear that it's easy. Okay, so we're done with recurrent.